Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Pharmaceutical Organic Chemistry, Paper 3. In the Unit 3, we are studying about heterocycles Part 1. In the Lecture 4, we will be studying about reactions of 5-membered heterocycles. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayamprabha, MHRD, New Delhi. The topics that will be covered in this particular session includes reactions of furans. Basically, we will be studying about electrophilic substitution reactions and Diels-Alder reactions of furan. We will also be studying about reactions of pyrrole and thiophene. In the case of pyrrole and thiophene, we will be studying about both electrophilic substitution reactions and regio selectivity of mainly pyrrole pyrroles. And we will also be studying some examples of drug containing 5-membered heterocycles. In this session, we will be studying about reactions of 5-membered heterocycles, mainly furan, thiophene and pyrrole. Their reactions mainly we will be studying. Let us recap what we have studied in the earlier sessions. We have studied some basic principles about electrophilic substitution, basically the reactivity which is based on the resonance energies. So we know furan, thiophene and pyrrole have lower resonance energy than benzene. In other words, they undergo reactions much more effectively compared to benzene, because benzene is highly stable, having a very high resonance energy, whereas these 5-membered heterocycles are having lower resonance energy. In other words, they are highly reactive. So that is one of the reasons these compounds undergo electrophilic substitutions under very mild conditions. In other words, these reactions are very fast and they are also carried out under milder conditions compared to benzene. One is the resonance energy. For the case of thiophene, furan and pyrrole, it is somewhere between 68 to 122 kilojoules per mole, whereas in the case of benzene, it is 152. That means benzene is highly stable compared to these heterocycles. And when we compare some of the reactions like nitration reactions, acetic anhydride and the nitric acid, concentrated nitric acid at 0 degree centigrade is sufficient to nitrate these heterocycles, whereas sulfuric acid and fuming sulfuric acid and nitric acid is required for nitration of benzene. And in the case of sulfonation, we have sulfur trioxide and pyridine at 0 degree. We can carry out the sulfonation of heterocycles, whereas fuming sulfuric acid and oleum is basically required for sulfonation of benzene. And in the case of halogenation, halogens at 0 degree can do the halogenation for heterocycles, whereas Lewis acid and heat is essential along with the halogens for the benzenes. And Wilsmeyer-Hack formulation is the easiest method to introduce formyl group, that is CHO group, into these heterocycles. DMO POCl3 is the reagent which can be used, whereas there is no reaction in the case of benzene. And benzene does not undergo Diels-Alder reaction also. And Friedel-Crafts alkylation and acylations require Lewis acid for benzene, whereas Friedel-Crafts alkylation is not a good method because it undergoes polymerization in the case of heterocycles, whereas Friedel-Crafts acylation is possible under milder conditions. So this is how we can compare the resonance energy with reactivity, and we will look at each reactions one by one in detail. So when we talk about electrophilic substitution, we talk about regio selectivity also. We will see some of the reasons why we get regio isomers in the case of heterocycles. So here we have alpha substitution, and here we have a beta substitution. So when the alpha substitution happens, the substituent, that is the electrophile, is added to the adjacent carbon, that is the carbon number 2, and when the beta substitution happens, the electrophile is added to carbon number 3. So these are all the various resonance structures which are responsible for this particular cyclization. We will look at individual steps more, in detail. So if we look at the reactivity order, Pyrrole reacts much faster compared to Furan, followed by thiophene, and benzene reacts very slower with respect to electrophilic substitution. Because thiophene is the most aromatic character of all the heterocycle, that means the 5-membered ring. So that is the reason it undergoes slowest reaction. Pyrrole and furan reacts under very mild condition. In other words, they react much faster. That's why we can even run the reaction under milder conditions. So the alpha substitution is favored over beta substitution because there are more resonance forms possible in the case of alpha substitution, and the charge is less localized, also applies to the transition state. So this is one of the reason the alpha substitution or the two position substitution is more favored. In some cases we also have beta substitution, that depends on what is the heteroatom we are involving, that means which heterocycle is involved. So depending on what is the heteroatom here, the selectivity changes, that means the regio selectivity changes. If it is nitrogen, that means if it is a pyrrole, the ratio of 2 to 3 is 4:1, and if it is oxygen, that means it is if it is furan, then the ratio is 6:1. Let us look at individual members. So first we will look at electrophilic reactions of furan. So the furan, when reacted with the DMF-POCl3, that is Wills-Meyer-Hack formylation condition, it gives the 2 substituted formyl derivative. When we do the reaction with acetic anhydride and nitric acid, we get the 2 substituted. This is the major product. So in the previous slide, we have seen that we have a mixture of 2 and 3 substitution. So the 2 substitution is the major product in this particular reaction. And when we do bromination at 0 degree centigrade, we get the 2 bromo derivative. And when we use the acylation conditions, that's what we had seen earlier. So acetic anhydride and H3PO4 and SnCl4 condition gives the selectively the 2-acyl derivative. And if you look at the mechanism for the nitration reaction, so the furan, when treated with acetic anhydride and nitric acid, gives this particular intermediate, reactive intermediate. So this is having the nitronium ion. So the nitronium ion is the electrophile which adds to the furan ring. So this adds to the second position, and this leads to rearrangement of the double bonds, that is realignment of the double bonds, and acetate group is also added as a acetate to the second position as well. So this is, if it is a 2 position, the ortho position of oxygen is having both the nitro group and the OAC minus group also is added. So this on treatment with the pyridine, that is the base, eliminates the acetyl group, that is the acetate group is eliminated to give the nitro 2 substituted nitro derivative. We have also mentioned about the Diels-Alder reaction, because unlike benzene, furan and other heterocycles have lesser resonance stabilization energy. So they behave basically like a diene rather than a aromatic system, completely aromatic system. So that is the reason furan undergoes Diels-Alder reaction. So reaction with maleic anhydride gives both the exo and the endo products are formed. And when we treat the same thing with acetylene dicarboxylate derivatives, we also get the aromatic Diels-Alder adduct is formed, which can give the aromatic system on heating. So this Diels-Alder adduct undergoes ring opening to give a aromatized derivative. So this is one way of converting furans into aromatic systems. Basically, in this particular case, we have a tri-substituted benzene is formed. Here we have a di-substituted benzene derivative is formed. So furan can be converted to aromatic system through the Diels-Alder reaction. And we have earlier seen sulfonation of furan using pyridine and sulfur trioxide gives the di-substituted derivative. So this is a very mild condition which gives sulfonation. And in the case of bromination, we have to be very careful with the conditions, because if the bromination is carried out at room temperature, this actually leads to polybromination. Whereas if we control the reactions by running the reaction at 0 degree centigrade with the bromine, the reaction gives selectively the 2-bromo derivative. And furan also undergoes addition reactions like normal alkenes. So the solvent for this reaction is very, very crucial, because this is one of the exceptional reaction. When the bromination is carried out with ether like dioxane as the solvent, we only get the brominated derivative, that is the 2-bromo derivative is formed. Whereas when the reaction is carried out in the presence of methanol, that is a protic solvent, this actually gives a acetal compound. So this is the major difference. So this is nothing but the addition of methoxide to the double bond. So that is how we get this cyclic derivative. So furan undergoes reactions which are typical of alkenes. So this is one such example. Another example is Diels-Alder reaction. So this way, even though furan is aromatic heterocycle, we say, this can also undergo reactions typical of alkenes. And let us look at a little bit more detail about the regio selectivity of the reactions. So we have position 2 and position 3 in the heterocyclic ring. When an electrophile adds to this heterocyclic ring, it adds to the position 2. So if it adds to the position 2, then the double bond is shifted towards this particular formation of bond with the electrophile, and that leads to the formation of a positive charge, that is a carbocation on position 3. So that is how we get a C plus ion here. This is quite unstable, so to stabilize that, the double bond is shifting from here, so that leads to a carbocation on adjacent to the heteroatom. If we go from the numbers 1, 2, 3, 4, 5, so this is the 5th position. So here a carbocation is formed, and now there is a lone pair on the heteroatom. So this heteroatom can give its lone pair for the stabilization of this carbocation, which leads to a positive charge on the heteroatom. So we have literally 3 resonance stabilized structures are possible when the addition takes place on the 2 position. So finally this loses a proton, that is, this proton is lost, and this heteroatom regains its lone pair of electrons, leads to the final product formation, that is a 2 substituted product. Whereas if the electrophile adds to the 3 carbon, so because these two are equally possible places for the addition, so addition of electrophile at 2 gives this product, whereas the addition of 3, if the electrophile is added to position 3, then we get a carbocation on the position 2. Again, this carbocation is just adjacent to the heteroatom having lone pair. So this carbocation can also be stabilized by the lone pair of electrons from the heteroatom. So the heteroatom gets a positive charge, and this can lose a proton to gain the aromaticity of this particular system. So now the addition took place at the position 3. So compared to position 2 and position 3, there are 3 resonance stabilized structures for position 2, and there are only 2 resonance stabilized structures for addition at position 3. So this is one of the reason the more stable product, that is the addition at the 2nd position, happens in the case of heterocycles. This is the predominant product, and of course in many cases even the 3 substituted product is also formed. So this is also called as the alpha substitution. This is called as the beta substitution. So by changing the reaction conditions, it is possible to get selectively, or the major product can be obtained between 2 and 3 positions. So running the reaction with acetic anhydride SnCl4 and 20 degree centigrade with phosphoric acid as a catalyst, we can selectively get the 2 substituted furan, acyl substituted furan can be obtained. So this is the condition. If you look at very carefully, the temperature is 20 degree and phosphoric acid is used as a catalyst in this particular condition. So this gives selectively the 2 substituted product, whereas if both the 2 positions are blocked, then only we get the 3 substitution very effectively. So this is one way of making the 3 substitution for acylation reaction, that is the electrophilic acylation. And here again, if you look at the temperature, it is 150 degree centigrade. So that means for getting the 3 acylation, we need to have 2 important conditions. One, the 2 positions, that is the alpha position of the heterocycle has to be blocked by some groups. Then the reaction has to be carried out at high temperature. So these are all the conditions by which we can actually force the reaction to 3 acylation in this particular case. And if we compare between thiophene, furan and pyrrole, for thiophene and furan, the 2 position is the preferred position for electrophilic substitution, whereas in the case of pyrrole, either 2 or 3 position both can be formed. And in the case of halogenation, thiophene and furan always gives polyhalogenation, but pyrrole, it's very difficult to control the halogenation. We will see some selective conditions by which we can actually brominate pyrrole. And the major advantage of pyrrole is like pyrrole can have substituents on nitrogen itself. So the presence of substituent on the nitrogen actually affects the selectivity. We can see how we can selectively make the reaction go to 3 position by choosing the appropriate substitutions on the nitrogen. So the 3 selectivity is easily possible in the case of pyrrole, whereas those are not possible in the case of thiophene and furan. And the thiophene basically reacts with electrophiles very similar to benzene, that is like aromatic systems. Whereas in the case of furan reacts like a diene. That's what we had seen earlier, like a Diels-Alder reaction and the addition reactions are examples of this one. So furan generally reacts like a diene because this is having the lowest resonance stabilization energy. And in the case of pyrrole, it is more reactive towards the electrophiles than benzene. So let us look at the reactivity of pyrrole. So what we generally observed is the pyrrole, even though it is a secondary amine, it fails to form adducts with methyl iodide. So no addition product is formed when methyl iodide is treated with pyrrole. Then the second observation is like the reaction of pyrrole with acetic anhydride fails to give the corresponding amide, that is 1-acyl pyrrole. So that means N substitution is quite difficult in the case of pyrrole. So what is the reason for that? If the reaction occurs on the nitrogen, then basically this is what happens. We have only one structure possible, whereas when the electrophile, whatever is the electrophiles, adds to the carbons, that is if the X plus adds to the carbon, then we have multiple resonance stabilized structures. So this is when there is a competition between N reaction on nitrogen versus reaction on carbon. The reaction on carbon leads to various resonance stabilized structures. So this is more favored compared to the reactions directly happening on the nitrogen itself. So this is one of the reasons the pyrrole does not undergo reactions selectively on the nitrogen itself. Of course, there are few reaction conditions by which we can effectively carry out this reaction, but in general, the N alkylation or acylations are really difficult in the case of pyrroles, unlike secondary amines, because secondary amines easily undergo addition reactions with methyl iodide or acylation reactions with acetic anhydride. Now, as I mentioned earlier, we can control the Regio selectivity by choosing a substitution on the nitrogen. So when there is a isopropyl silyl group attached to the nitrogen, then this is a very bulky group and it prevents the electrophile to attack on 2 position, that is the ortho position attack, or in other words the alpha position attack is prevented because of the bulky isopropyl silyl group. So that leads to selectively the 3-position substitution, that is the beta substitution is possible. In this particular case, the nitration occurs on the 3 position. And when we have SO2 group attached to the nitrogen as shown here, so here again this is the typical Friedel-Crafts acylation conditions. So here the reaction again occurs very selectively on the 3 position. So this is a major advantage with Pyrrole. So by changing the substitutions on the nitrogen, we can selectively prepare the 3 substituted derivatives. This is not possible in the case of furans and thiophenes. Now, a major question we have to answer, because we have seen so far many reactions, the nitrogen does not undergo alkylations or acylations like a secondary amine, and this also undergoes reactions mainly on the carbon only, that is aromatic systems of the heterocycle only undergoes reaction and not on the nitrogen. So this puts a question whether the Pyrrole is acid or a base. So there are few evidences to show that Pyrrole is an acid, because if in the Pyrrole the nitrogen is having a proton, so if the proton is abstracted by a strong base, then we get the anion. So this anion can now give its this pair of electrons to the ring system. So we have various 1, 2, 3, 4 different carbanions are all possible in this particular system. So in other words, if a Pyrrole is the proton is abstracted or removed on the Pyrrole, that leads to various resonance stabilized structures. So this is one of the reasons the Pyrrole behaves like an acid. And here are some of the examples of the reactions where Pyrrole behaves like an acid. So the Pyrrole, when treated with a base, either potassium hydroxide or a strong base sodium hydride. If you use sodium hydride, this abstracts the proton, and there is another hydrogen here. So these two are lost as a hydrogen gas, and then we get this particular anion. And if we treat the Pyrrole with the potassium hydroxide, then again we get this proton can be abstracted by the base. So this anion can undergo acylation reaction and alkylation reaction. So this is in contrast to the direct reaction of Pyrrole with alkylating or acylating reagent. So this is one of the important things you have to remember, because Pyrrole does not behave like a typical secondary amine. So acylation and alkylation are not possible directly on Pyrrole, whereas this Pyrrole nitrogen is having the acidic proton. So that acidic proton can be removed by a base, which leads to acylation and alkylation conditions. So this is one of the reasons we say Pyrrole behaves like an acid. Let us look at why Pyrrole is a weak base. So this lone pair of electron on the nitrogen is actually involved in the aromatic pi-aromatic system for the heterocycle. So that is the reason this lone pair is not available on nitrogen, so it is not a strongly basic one. And again there is one more reason, because if we look at this particular reaction, when electrophile is added to the nitrogen, what happens is the entire system becomes non-aromatic, because the lone pair on the nitrogen is now no longer available for the pi aromatic system formation. So this is a very high energy demanding step, in which the highly unstable non-aromatic nitronium ion is nitrogen having positive charge is formed. So this is a quite unstable step, and this is generally not happening. So that is the reason the Pyrrole is behaving like a very weak base. The first one is the lone pair of electron on the nitrogen is actually involved in the pi aromatic system, so the nitrogen is no longer basic. And the second thing, even if electrophile is added to the nitrogen, that completely destroys the aromatic system. So these are various reasons due to which Pyrrole is a very weak base. And let us look at some of the electrophilic reactions of Pyrrole. The first one is like a Wilsmeyer-Hack formylation reaction. So the Pyrrole undergoes formylation in the 2 position to give the formal derivative, and the reaction with acetic anhydride and the concentrated nitric acid produces both the 2 and the 3 substituted nitro derivatives. They are formed in 4:1 ratio. And bromination using N-bromosuccinimide is a very mild condition which generally gives a monobrominated derivative, whereas bromination in the presence of bromine and at 0 degree actually gives the tetrasubstituted or the polysubstituted bromination reaction. So this is what I mentioned earlier, like by controlling the reagent which is used for the reaction, we can selectively make the 2-bromo derivative or the polybromo derivative in the case of pyrroles. And the reaction with the triflic anhydride gives the corresponding acylated derivative, and the sulfonation using sulfur trioxide and pyridine gives the 2 substituted derivative. So these are the various reactions, electrophilic reactions of pyrrole. Let us look at Manicure reaction. So in this particular case, pyrrole reacts with formaldehyde in the presence of a secondary amine to give the corresponding Manicure derivative. So this reaction mechanism is actually shown here. So this is one of the addition reactions of pyrrole. And pyrrole can also be converted to porphyrins. So this is very similar to the addition reactions what we have seen in the previous slide. So here we have the hydroxide derivative which loses a water molecule, and this again undergoes multiple cyclization reactions with pyrrole to give a non-extended aromatic compound as shown here, which can be converted to the 18 pi electron system. So this is what is called the mesocarbon here. So a methane carbon connecting 4 pyrrole ring is what is called the porphyrin moiety. So this can easily be formed because of the extended pi electron system or the aromatic stabilization which is gained by the formation of alternate double bonds, and this molecule is also planar molecule. So this is one of the reactions of pyrrole. And let us look at some of the drug derivatives from the heterocycles. The first one, Curon, involved as a drug molecule. So ranitidine is one of the blockbuster drug in the history. This is generally used for the H2 receptor antagonist, and it lowers the stomach acid levels, and basically it is used to treat stomach ulcers. So this ranitidine has a furan moiety here. So this can be prepared from furfural. So this is one of the drug derivative which is having the heterocyclic ring, that is the furan, as one of its component. The various reactions are given here for the formation of ranitidine. And we also have nitrofurantoin. This is used to treat urinary tract infections, and it is also an antibiotic. So this also has a furan ring. And there is another drug, furosemide. It is used to treat high blood pressures and edema. It is a diuretic. This is also having the furan ring as its component. And cefuroxamine is used to treat infections like bronchitis, Lyme disease. This is a cephalosporin antibiotic. This is also having the furan ring as one of its components. So these are some of the examples of furan as drug derivatives or drug compounds. And let us look at pyrrole based drugs. So tolmetin is a non-steroidal anti-inflammatory drug. It is mainly used for the treatment of reducing the hormones that cause pain, swelling and tenderness. So this is the pyrrole unit which is present in this particular drug. And we also have aloracetam. This is a neotropic drug. This is used for the treatment for Alzheimer's disease. So this is also having a furan ring as one of its component. And the next compound which is atorvastatin calcium or the Lipitor is a blockbuster drug, and this was the world's best selling drug ever with more than $125 billion of sale over 14.5 years. This is marketed by the company named Pfizer. So this drug is basically a cholesterol lowering medicine. This is having the penta substituted pyrrole. See, if you look at the central point, So this is the penta-substituted pyrrole unit, which is the crucial part for this drug, and this drug is generally used to reduce the cholesterol. So basically, beta-hydroxy beta-methyl glutarate CoA reductase is the key enzyme which is used in the regulation of cholesterol synthesis. So this side chain unit is very crucial for the control of the HMGR inhibition activity. So this is what is the structure of atorvastatin calcium or Lipitor, and this compound has the central pyrrole unit. And we also have couple of thiophene based drugs. So Pyrantel is a medication used to treat a number of parasitic worm infection. This is a thiophene unit which is present in this drug. And we also have ketotifen. It is an antihistamine drug for the eye treatment. So this generally treats the allergic symptoms by the blocking of certain natural substance, that is the histamine. So this is basically antihistamine, so histamine blocker. So this has the thiophene unit present in this particular drug. So these are the various drugs based on thiophene. Let us recap what we have studied so far. We have studied about the various reactions of furan. So how furan can behave like a diene, as well as it can also undergo electrophilic substitutions which are similar to benzene. And we also have studied about the Diels-Alder reactions and how furans can be converted to benzene derivatives. And we also have studied about the reactions of pyrrole and thiophene, especially the regio selectivity of pyrrole, where alpha or beta substitution, how we can control the reactivity by changing the reaction conditions and the substitutions on nitrogen, how we can selectively prepare either the alpha or beta derivative we have seen, or in other words 2 and 3 position substitutions can be selectively controlled. That we have studied. We have also studied about some of the examples of drugs containing 5-membered heterocycle. Lipitor is one of the important drugs we have studied. So with this we conclude this particular session. Thank you.